Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So what we're going to talk about today really is we're going to start with going over some theory and fundamentals. This really has to, in order to look at beamformers, you need to have a little bit of antenna theory behind you, since the two of them work hand in hand. We will then go through some different topologies, different ways of methods of beamforming and different ways to build them. Then we'll talk about a couple of applications as we're going through there, talk about some TRM differentiators, and then sum it up at the end.
Terrific, thank you. And maybe next you could define a beamformer in a more detailed fashion compared to the layman's version that I shared earlier.
Sure. So a beamformer essentially is a device that distributes a signal out to an antenna network. So the antenna network can direct the energy in the direction that the end user needs. Systems that require beamformers almost always have multiple inputs into the antenna system, which means that they are by nature an array antenna, and that the beamformers that TRM builds are passive beamformers, and therefore they are reciprocal, which means you generate the same beam either in the transmit mode or in the receive mode. So that's also another important differentiator there. Beamformers typically are co-located with the antenna, which is something I think that from an environmental standpoint we have to consider, since usually antennas are out in the rain. We have to make sure that these beamformers are environmentally secure. The difference between a receive and a transmit mode really has to do with, it's really semantics. With the transmit mode, the beamformer sets up the amplitude and phase required for the antenna to point a beam in a specific direction. In the receive mode, signals that are being received due to time and space have a different phase relationship with them as they reach the various elements. And what the beamformer does is it recombines that energy so that we can actually effectively combine and have a good signal in a specific direction.
Okay, thank you, Shaun. You know, I've also heard you refer to antenna theory. Can you explain a little bit about that?
Yes, absolutely. So in order to basically like I mentioned at the opening, in order to have an understanding of beamformers, you have to understand a little bit how antennas work. Now, antennas, by their nature, take a signal that is on a transmission line and translate it into a wave that crosses space and time. The energy goes from the antenna and spreads out over space. By definition, an antenna cannot create energy, so therefore its gain cannot exceed 1 or 0 dBi in antenna terms. That is, if the energy is radiating out in all directions simultaneously. That's the definition of a gain of 1 or 0 dBi, is that the energy is radiating equally into a sphere, equally in all space. When we talk about antenna gain, that is taking some of the energy in directions where we don't really want it to go, and refocusing that energy over into a particular direction. So if you think about a balloon, which takes the energy that you blow into it and expands the balloon out equally in all directions. If you grab one side of that balloon and give it a good squeeze, you'll see that the other side kind of pops out. That is what we talk about gain or adding directivity to an antenna aperture by taking energy and adjusting the amplitude and phase taper and where the energy is going and directing it in one direction. We can have more gain than one in a particular direction, and that's when we talk about gain. Now, how do we actually achieve that is the next topic that we're going to talk about.
Okay, so maybe then you could tell us a little bit more about how the antenna theory aligns with a beamformer or with the process of beamforming.
Sure. So, like I said, in order to really understand how that gets done, you need to know a little bit about antenna theory. The example that I'm going to go through here, which is basically illustrative of most array antennas, is that if we have two elements, how does that signal combine, and why does it combine the way that it does, and what is the effect of amplitude and phase or time delay have an effect on where that beam is actually steered. Basically, and what we're going to do here is we're going to take two antenna elements. We're going to have an in-phase power divider, or just a regular standard power divider, and a phase shift element. With those three elements, the two antennas, the power divider, and the phase shift element, we're going to build a simple beamformer.
Okay, then could you maybe tell us a little bit more about the delay elements?
Sure. So in the illustrated example here, where we have a RF source that is perpendicular to the antenna array, by nature of the energy going through time, both antennas are going to receive the energy at the same time, which means the received energy coming in from that wavefront is going to hit the antennas at the same time. Therefore, the energy will be in phase with each other. If we add those two energies together with a simple power combiner, the combined signal will take the energy received from antenna 1 and antenna 2 and sum them vectorially, and that you will receive twice the signal that what you receive that if you just had one antenna by itself. This, by its nature, creates what we call a bore-site beam, which means that both antennas are receiving energy perpendicular to the array itself. And what happens when you sum this vectorially, since there is space between the two antennas, if energy was to be received at an off angle or something other than bore-site, there would be some subtraction of energy because the summing would not vectorially add up the same way that it does if they're lining up on bore-site. Once you get a little off angle, then the energy would actually subtract a little bit. This subtraction and this addition is what creates the ability to be able to steer the antenna array in a particular direction.
Okay, so what if the antennas receive the signal at different times?
Okay, so that is this next illustration right here. So as I sort of alluded to just before, whereas if the antenna is not perpendicular, what you see there on the graphic on the right-hand side of the screen is that the signal will arrive at those two antennas at different times. So what happens is then if we do not have a delay network in the system, the signals will not add efficiently. In which case, when we go to add some of these signals, there will be some subtraction of the signals. The way that we compensate for that is we add a delay element on the antenna that is receiving the signal first. And therefore, by the time the energy gets down to the signal combiner, they are now adding in phase or adding efficiently. The net result of this is that you get the scan beam now that is on the lower left-hand side of the screen, where the beam is now steered towards the source. In the same way that that the vectorial summation of those two signals happens very efficiently with that delay network set, so that the delay is equal to the arrival time difference. Conversely, had that source been on the other side of the screen with the same delay network, that delay network would actually further delay the arrival time of that second source, which would actually make it subtract even more than it would ordinarily. This effect of having the beams sum so that we get nice addition in the direction where we want it and have subtraction in other areas is what creates the beamformer theory. And this allows us to take antenna elements and make them very directional in one direction. By that I mean that they will sum quite nicely in one direction, but they will subtract in most other directions. And by doing this, we can create a very narrow, high efficiency beam in any one given direction.
So from what I'm gathering then, are there different beamformer types or configurations?
Absolutely, and I think one of the ones that TRM works with quite commonly is the Butler matrix. Butler matrix is a very common sort of application of an antenna beamformer. And in order to create these beamformers, they're built out of building blocks of hybrids and delay elements. There are really two separate types of delay elements that are used in beamformers. Neither one is better or worse than the other. It really depends on the application, the antenna's array spacing, as well as whether or not the beam needs to steer or move along with frequency variation, or whether you want it to stay put. And that'll determine whether or not for the delay element, whether you use a time delay element, which is something like a physical cable length, or whether you want to use a phase delay element, which is a phase shifter. Now, the difference between the two of them is that the time delay or the cable length at any one frequency will have a certain amount of phase delay associated with it. That phase delay will change with frequency, but the time of the signal will remain constant. The difference between that one and a phase shifter, the exact opposite will happen. As we change frequency, the phase relationship will remain constant, but the actual time going through the network will change according to frequency. They both have advantages with said one is neither better than the other. They create different sorts of scan beams in the actual application.
Okay, and I see the bullet at the bottom here says that there are many variants of this type of beamformer. Could you describe some of these variants?
Yeah, sure. So the most one of the simpler Butler matrix is called the 4x4 Butler matrix. And this particular matrix, you will see that there are 4 antennas and then 4 beam states. As I previously mentioned with the scan beams, the antenna pattern on the lower left-hand side of the screen shows the 4 beams that are created from a linear array using a 4x4 Butler matrix. You will see the 4 lobes associated with there. Each output of the Butler matrix creates an individual lobe. Now, for an actual application of this sort of matrix, if you want to switch between those 4 lobes, all you need to do is put a 4-way switch on the output side of that Butler matrix and switch between them, and you can generate 4 individual distinct antenna patterns using a passive network up to a fixed antenna array. Now, we also mentioned that the antenna array itself, which is where the scan beams actually end up, are very much dependent on the element spacing of the array. In the example here that is drawn up on these particular 4 beams, the antennas are relatively close to each other. And I can tell that by the fact that the 4 beams are all looking pretty much not too far left or right of bore site. Had these antenna elements, individual antenna elements, be spread farther apart from each other in this kind of axis, then each of these lobes would bend down farther and be closer to the horizon. So instead of having the 2L and 2R being up there at, say 30 degrees off of vertical, those lobes can go right on down, right, even touching the horizon, depending on that individual element spacing. So the individual lobes can be shaped based on antenna element spacing. The other thing also keep in mind also is if you have a fixed element spacing, you can change where those lobes end by changing your phase adjustments across your elements. So that's kind of the balance and trade-off that we have to work with for these sort of beamformers. We have to work with the antenna designer to fully adjust both the inter-element spacing, which sets up the delay, the path delay for various off angles, and then the beamformer needs to be adjusted to compensate for that inter-element delay.
Okay, how about some of the additional variants? Could you talk about those a little bit?
Sure. So another variant of the Butler is what we call the 8x8. Now, the 8x8 Butler creates same sort of idea, except it uses 8 antennas instead of 4, and it can create 8 individual beams. Traditional Butler sets up 4 left and 4 right. Again, these beams have a narrower beam width, but there are certainly more of them to select from. Again, the same basic idea as far as how it is. Also, you notice the level of complexity that gets picked up in the block diagram on the upper right from the previous one, whereas before we just had a very simple network of 4 hybrids and 2 phase shifters. You can see here we've picked up a substantial increase in the complexity. The 8x8 Butler uses 12 hybrids and quite a few phase shifters.
So based on the way you described that, I assume that there are other variants that are not associated with the Butler matrix?
Absolutely. The Butler matrix is really just one particular subcategory of passive networks. Another very popular one that TRM builds is something called a monopulse comparator. Now, a monopulse comparator is typically used for tracking antennas. And in order to be able to build a monopulse comparator, you need a 4-element antenna array at a minimum, and it needs to be laid up in a 2x2 configuration. By that, if you take a look on the sort of in the middle of the screen, down on the bottom, you see the antenna element configuration there, where you see the ABCD block. That shows the 2x2 antenna element configuration. What happens here with this is that this hybrid network establishes sum of energy and difference of energy between those 4 antennas, and it creates really 3 distinct antenna patterns that you see on the lower left of the screen. The dark blue pattern there shows the sum of the 4 antennas, and basically that takes the input from A, B, C, and D and sums them all in a Boresight fashion, which means that all that energy coming in and all the data coming in will be summed when the antenna is perpendicular to the source. There are 2 other modes that get generated out of the monopulse comparator. There's the delta as and delta L outputs of the beamformer, and they both create the purple line that is on the graph. And what's interesting about the purple line is that there is a null on Boresight, as opposed to getting energy on Boresight. Nothing will be received on those 2 outputs when the antenna is on Boresight. When the antenna goes off of Boresight, you will then begin to see energy coming out of those two ports. So what is done is that the data on a monopulse comparator, which is usually where the signal is coming down, and really the information that's being received is maintained on the sum port, and the delta L and delta as outputs are fed into the antenna pointing subsystem, and this tells the antenna whether or not it is actually being steered to true Boresight. And if the energy on the delta L or the delta as port starts coming up, the servos will drive the antenna to maintain a null, and this is basically with a null tracking algorithm. They can make sure that the antenna always stays on board site to make sure they get maximum amount of data, maximum signal to noise ratio for the data coming in, and make sure that they don't lose the signal. Monopulse comparators are not only used for data for earth stations for tracking satellites, which is one of the primary uses. These are also used on some other tracking systems for radar. If you have a mechanical gimbal driving the phased array for determining mechanical direction, a monopulse comparator very often is used in addition to that. So if we have any kind of a tracking radar, for example, that does not have a fully active phased array, you can rest assured that there is a phase comparator in there used as its tracking element.
Okay, and what other types are there that you might want to list?
There are lots, and one example here. This is an example of a sum difference network, which is really thought of as a single dimensional monopulse comparator. TRM builds this particular one for a military application, but this particular one over here has 8 antenna elements input. The antenna elements are set up in a linear array, and really what this particular part over here is looking for is we're looking for the sum or the data to make sure that the information being received is maximized, and then the difference tells you how far off of bore site, or how far off of the nose of the plane the information is coming from. This particular antenna array is looking for whether or not you're tracking something or flying directly at it. It's actually part of a landing system. Therefore, we want to make sure that the plane is flying directly towards the runway and not flying off the side of it. Therefore, this particular system wants to make sure that that the plane is indeed pointing at the runway as it's coming in and being approached. Therefore, this is a very good application for this type of a beamformer, sort of a one-dimensional, because all we really care about is that yaw plane, making sure that the antenna, that the aircraft is coming in perpendicular to the runway. This particular beamformer also has an additional element, in that the amplitude across all 8 elements are what we call Taylor weighted. Taylor weighting is nothing more than a mathematical function that adjusts the power going to the individual 8 elements in an effort to reduce the side lobes, to make sure that there's no extraneous energy poking off to the sides that might interfere with the main beam coming in. So that is something else also that that is very often done. As you know, with a lot of antenna theory, you don't always want an equally illuminated aperture for optimum performance, especially if you want to reduce your side lobe levels. I should mention a little bit about what side lobe levels are, and they are any antenna pattern will create a main lobe or the main focus of where the energy is going. A lobe is an additional smaller off-axis reasonably efficient area that can receive energy as well. It is normal to want to reduce the side lobe levels as much as possible, therefore, and maintain the purity of the data coming from the particular direction you're steering to. So it is almost always, from a application standpoint, we want to maintain very low side lobes. Aside from actually going in there and designing the individual antenna apertures themselves for lower side lobes, you can further decrease those side lobes by applying a power taper across the aperture, which will further decrease those side lobes.
Okay, and if I've understood this correctly, then I assume that the variants are selected based on the application?
Absolutely. We do so many different things and are really applying to how the network gets configured. It's all about the application. It's all about the exact antenna configuration. There are so many variables that drive into this, which really kind of drive into this next point, is that there are lots of variations of beamformers. It's the ones that are shown on the screen here. None of these are your classical Butler matrix, monopulse comparator, sum difference networks, but these are all located directly behind the antenna. And really they're used for a variety of applications. These are all multifunction modules, and therefore they fall under the umbrella of a beamformer, although they may not have a beam steering point to them. Very often these are used as signal injection test points. A lot of these systems, you want to be able to make sure that you can calibrate out, for example, phase differences over temperature, cable length differences that are run through the aircraft, and other sorts of things, especially if you're dealing with interferometer-based systems where phase relationships between elements are critical for determining angle of arrival. So we build quite a few parts that use for those sorts of applications, and we loosely call those beamformers as well. The other thing also we use beamformers for very often actually is just creating the particular amplitude and phase difference required for specific antenna feeds. Log periodic antennas, for example, do want to have a 180-degree phase shift as part of that infrastructure. We will very often build into our beamformers those sorts of phase shifts so they become multifunction modules in that way as well.
So what about some of the different technologies that are associated with beamforming? Can you tell us a little bit about that?
Sure. I mean, just like any of the other products that TRM builds, beamformers can be built using literally any technology. And, what TRM does is and of course we mix technology depending on the frequency, other performance parameters. We use lumped element designs with ferrite transformers, wire wound transformers, capacitors. We also utilize distributed circuits as well, going to microstrip, strip line, coax, and all the other technologies. Like I mentioned in other webinars here. Really, these things we use virtually every technology except for waveguide here at TRM.
Okay, and then maybe you could identify some of the typical applications then.
Sure. So, passive beamformers are really, they almost always go right behind the antenna because these are networks that really steer the energy to the array and then do some real-time processing to do some beam shaping. Most of the time, since they are located near or by the antenna, they're usually in a place where they will see some severe environments. They're going to be outside. They're going to see pressure. They're going to be on sometimes some high vibration areas, buffeting areas on the aircraft. Therefore, these things need to be designed to be very robust. I will say that whereas there are typical configurations for beamformers, there is no quote unquote standard level for beamformers. Depending on the frequency, the antenna array spacing, these things really, they're all over the map as far as what the requirements really end up being. Part of what passive beamformers actually do quite well at is looking across multiple sectors at the same time, since you can have multiple beams being simultaneously generated. Depending on how you set up your electronics behind there, you can use that for looking for threats, and therefore, so for a lot of EW applications where we're looking for threats across a very wide area, passive beamforming can be a very effective way to scan a sector, as opposed to going in there with an active phased array, which typically gets very, very specific about where it looks, which can have a lot of great applications. But sometimes it's not always the best way to do it. Sometimes going across with a broad swath, looking across broad areas. If you're looking for to see if a threat is present at all, very often can be more effective than looking very, very focused across a bunch of small areas. In which case, by the time you actually get to the sector where the threat is, you may have missed it.
Okay, so speaking of customization there in the final bullet, maybe you could share some of the innovations or enhancements that TRM typically makes so that the beamformers fit each application.
Sure. What TRM does with all of our products, of course, is we go in there and we like to speak to design engineers to see exactly what it is that they're trying to do, and this is really part of our differentiation. What I will say is that beamformers are almost always custom because there is something that is very unique about the application, and very often we go in there and we talk about the different technologies that we want to use. No one is better than other one. No one technology is better than any other technology, and really we want to go in and make sure that we pick the right technology. We have to find out whether phase flatness is most important to the customer, amplitude, insertion loss, whatever those parameters are, we need to know that so we can pick the correct technology. And basically, to reiterate it again, TRM does not cherry pick which technology we use. We don't have a favorite technology. We use whichever one's the best for the customer. And again, we use pretty much every technology except for waveguide.
And I assume that screening must also be involved.
Absolutely. And if you get into a lot of these sort of applications, Paul, what's really important is that we meet all the requirements for the customer. Very often, as you go through these requirements, it's not just building the hardware, it's making sure that we validate that the parts meet the requirements over the environments. So therefore, we are quite happy to go in there and do whatever custom screening or qualification validation that our customers are requesting.
And what about packaging?
Again, packaging is a big part of it. We have to make sure that the parts, can survive the environments that they're looking for, where the connectors are located, especially if you're talking about a lot of these beamformers that are interfacing directly to the antenna aperture. You'd be surprised at how often we get requests for connector spacing, which may seem very odd to most people. But if you look at the entire system, they set up the connector spacing, for example, to match up to the element spacing. Therefore, they can have a direct blind mate connection from the beamformer directly up to the aperture, which makes a lot of sense from a system standpoint, although we do end up with some very odd connector spacing by doing that.
Okay, well, gee, that's a lot of good information. You had mentioned earlier that maybe you'd like to wind up with a summary, so maybe you'd like to summarize for us.
Sure. Now, the top summary here really is that beamformers act as the interface between the antenna itself going back to the rest of the avionics. And really, because of that, there's a wide variety of beamformer types. We like to talk about, the Butler matrix. That's kind of a favorite one for us, as well as the monopulse comparator and a few others. But realize that there are lots of other beamformers that don't have formal names. And these are all things that we certainly like to go ahead and speak to the customer to find out really what it is that their needs are. The other thing I really keep in mind is that the beamformer needs to be designed really in concert with the antenna aperture design. Really, there's lots of variables that you get into when you start designing antenna apertures and phased arrays, and all those variables need to be taken into account when designing the beamformer as well, because they work together as a system. If you change one thing on the antenna array, the beamformer will behave differently when hooked to it in the system. Therefore, all those variables need to be looked at.
Well, terrific. Thank you once again, Shaun. And before we take a question or two, I would just like to say that once again, I think you've done a very nice job at explaining not only the innovations that are required, but the lengths to which TRM goes, and in particular to meet with some of the customers' design engineers to identify the best solutions. So thank you for that. One question that I did receive, you had mentioned that beamformers are almost always customized. Is that based on the antenna spacing, or are there other elements?
Yeah, the antenna spacing is huge on that, Paul, and that's really something I think that people really need to keep in mind. The antenna array spacing, as well as other mechanical variables, really drive the way we design the beamformers. The other thing also to keep in mind, there will be scanning of the beam that occurs due to the wavelength changing as frequency changes across any given aperture. The way that compensation happens, or the way that the beam scan angle happens that varies over frequency is handled is very specific to the application. And that goes into whether or not we put in a fixed time delay or whether we put in a fixed phase delay. Those sorts of variables can make a huge difference in the way that the overall system performs. TRM can handle either way, and it's really a matter of going in there and really determining how do we want that net frequency dependent scanning to be handled, and that's very much dependent on the actual system and the system requirements, and very well it may even come into how the way the software is going to handle that's driving this as far as to how it's going to interpret that data. So a lot of system level questions need to be integrated together, and they all point to little variations in the beamformer that need to be addressed.
Okay, There are a couple of other questions, and we will address those by email. I want to thank you all once again for joining us today. If you are a customer and you would like to ask more questions directly, please feel free to call the engineering hotline, which is there on the screen, 888-677-6877. The goal is here that we would like to learn more and understand your ideas, and then maybe help you complete them by turning them into some kind of practical solution. And if you are one of our field sales representatives, then you know that your calls are welcome anytime too, and that you can submit questions directly through your CAM or through the sales rep portal. Thank you all so much. And once again, Shaun, always a pleasure.
Thank you very much. Have a good day.